Welcome back. So as promised, in this video I'll show you an example of how to integrate over a normal domain. So let's consider one of the normal domains that we have already seen. Specifically, we'll use the domain D, all x in R2, where minus 1 over the square root of 2 is less or equal to x1 is less or equal to 1 over the square root of 2. And x2 is bound below by x1 squared and bound above by 1 minus x1 squared. Now what that looks like, just as a quick reminder, what you have here is two parabolas. There's this lower bound parabola, x1 squared. That looks like this. And then there is the upper bound, 1 minus x1 squared. That looks like this. So the set D is everything in between those two. Meaning exactly this here, that is a set D, of course, including the bounds as well. And here's the x1 values. This is minus 1 over square root of 2, and this is plus 1 over square root of 2. That's just the points where these two parabolas happen to intersect. Okay, so this is the normal domain D. And what we're going to do is we're going to compute the volume of that set. So we want to compute the volume of D. And we do that by integrating the 1 function over the set D. Okay, so the volume of D is the integral of 1 dx over D. And now let's see how we can express that using that normal domain description here. So as I said, the outer integral is always that with the constant bounds. So the outer integral in this case needs to be the one with the x1 bounds, these two here. That's minus 1 over square root of 2 to plus 1 over square root of 2. And then the inner integral is over x2. So let me write x1 here. And x2 has a lower and an upper bound. So the lower bound for that x2 integral is x1 squared. The upper bound is 1 minus x1 squared. And as you can see, the bounds depend on the variable x1, but of course not on x2, because that's the one we want to integrate out. And we're just integrating the function 1. So that is dx2, dx1 in that order. Okay. We'll keep the outer integral. We will compute the inner one. So the integral of 1 with respect to x2, that's easy, that's just x2. And then we need to substitute the bounds. Lower bound is x1 squared, upper bound is 1 minus x1 squared. So let's compute that. So again, we'll copy the outer integral. I first want to simplify the inner expression before we compute that. And then we need to do the usual thing, which is we'll evaluate the integral at the upper bound minus at the lower bound. So here we have 1 minus x1 squared minus x1 squared. dx1. So that is one more simplification step. Again, we copy the outer integral here. So that is 1 minus 2x1 squared dx1. And now we can actually evaluate that integral. That only depends on x1 now. So we've gotten rid of the x2 variable by that point. And what we get here is x1 minus 2 over 3 x1 to the third. And the bounds are minus 1 over the square root of 2 and 1 over the square root of 2. Okay, again we substitute the bounds. So upper bound first, that is 1 over square root of 2 minus 2/3 times 1 over 2 square root of 2. And then we subtract the lower bound. So that's minus 1 over square root of 2 minus 2/3 times, and then we have minus 1 over square root of 2 to the third. So that's again a minus 1 over 2 square root of 2. Okay. So altogether, what do we get? Let's see, we have this 1 over square root of 2 minus the 2 here. This cancels out nicely. So there's minus 1 over 3 square root of 2. Then we have minus minus, that one cancels out. So there's a plus 1 over square root of 2. And then we have this, we have this minus and this minus, those cancel out, and this minus. And again, the factor of 2 will cancel out. So we have a minus 1 over 3 square root of 2. Okay, so altogether, how many square roots of 2 are there? Let's see, we have something like 1 over 3 square root of 2. First is 1 over square root of 2, so that's 3 over 3 square root of 2. And we have that once again, so that is this factor and this factor. And then we have this factor also twice, so we have a minus 1 and another minus 1. Okay, so altogether, well, that here is 6 minus 2, that's 4. So we get 4 over 3 square root of 2. And finally, let's make the denominator here rational. So we extend by square root of 2, that's 4 square root of 2 over 3 times 2. Or let's cancel out one factor of 2, then we get 2 square root of 2 over 3, or 2/3 square root of 2. Okay, so that is the area of that set D, that normal domain here that we defined in the beginning, this one. And of course, in this case, we just integrated the very simple function 1 to start with, and then it got more complex with the first step. Of course, we might also start with a more complicated function like a polynomial, for example, integrate that. The steps will be pretty much the same, just the results will be a little more complicated then, of course. Okay, so that's how you integrate over a normal domain using the description for the normal domain. And again, if the description is not given and you need to come up with that, then of course there are usual several ways to do that. So this might not be the only way to describe that particular normal domain. And depending on what description you come up with, the integrals and maybe the order of integration will be different. The end result should, however, always remain the same. So if you try two different descriptions and get different results, then you either messed up with the integration step somewhere, or one of your descriptions, or at least one of your descriptions, is wrong. Okay, so coming up with a good description is usually at least 50% of the work to evaluate that integral. We'll talk a little more about that when we get to coordinate transformations, because of course you can also try and describe normal domains in different coordinate systems, but that's the topic of one of the upcoming videos. And you find more practice examples on the current exercise sheets. So have a look at those if you want to get more practice in integration over normal domains. That concludes this topic. I hope you learned something new, and I'll see you in one of the upcoming videos. Bye.